Everyone, to tonight's session on electrophilic aromatic substitution. First, before we go into the reaction, let's talk about what this actually means. When we're looking at something electrophilic, we're looking at an electrophile, which I like to write as an E+. This is something that is positive or partially positive and attracts electrophilic, electron loving. Aromatic substitution is when we're substituting onto an aromatic compound, for example, benzene. The benzene ring is a cyclohexane with 3 alternating pi bonds for a conjugated, resonating, very stable system. And the reactions are going to look almost like an alkene reaction, except with one major difference. If I take a simple alkene, for example, 2-butene, and I react it with something like Br2 in an inert solvent such as CCl4, you should remember from your Orga-1 reactions that I will get halogenation. I will get one bromine adding to one face and one bromine to the other face in an anti-addition, where 2 bromines replace the pi bond. We broke the pi bond. This carbon held the pi bond. This one held the pi bond. They both got a bromine. If I try to do the same reaction, once again using Br2 in CCl4, and assuming I have excess Br2, enough to react with every single pi bond, am I going to get each pi bond breaking for 6 bromines adding? Am I going to get 2 bromines where one of the pi bonds break? What am I going to get? Well, I'm going to get absolutely nothing. No reaction. This is not going to work. And the reason for that is a pi bond is definitely reactive. A pi bond is a very good nucleophile, and it will reach out for something nearby if it's attracted enough. But in the situation of a benzene ring, because I have the stability that comes with aromaticity, and if you're not comfortable with aromaticity, I put a link down in the description to my aromaticity videos. The aromaticity, the conjugated system, is so stable, and the electrons that are resonating within the system are so happy to be resonating. They don't want to break out of that comfort zone. They don't want to attack anything. You have to entice them out with something that is so much more electrophilic than Br2, with something that is so reactive that it's enough to overcome the stability of aromaticity. And that is what this chapter is all about. So while I start writing out the mechanism for the basic EAS reaction, let me know in the comments if you're currently in Orga-1, Orga-2, or if you're studying organic chemistry for something else. While you type that in, and if you're watching the recording, I still want you to let me know in the comments, and I do try to go back and read them all. If I have an aromatic ring, we'll keep track of the pi bonds in different colors so that we can see what happens. And this time, instead of reacting with just something simple that would react with an alkene, I bring in a super electrophile, which I'm going to go into detail soon with specifics. But the idea of a super electrophile is that I have something so positive, so reactive, so unstable that the pi bond is so attracted to it, it actually breaks out of the aromaticity. The pi bond will reach out, and in this case it doesn't matter because they're all the same, and grab that super electrophile. When that happens, I will get the same structure, except one of the pi bonds now is broken. Let me just copy that so I don't have to keep redrawing the benzene. So the pi bond with the green pi bond with the red electrons is the one that broke out. So we still have the blue pi bond and the purple one here. I can put the electrophile either at the top or the bottom in this case because I have nothing else on the molecule. Later, I'll show you what you do if you do have something else on the molecule. The pi bond broke from 2 carbons. One carbon got the electrophile, and don't forget they also have hydrogen atoms. So the one at the top has a complete octet, it's perfectly happy. The carbon here that lost the pi bond and got nothing in return now has a carbocation. Now, technically, this carbocation is not so bad. It's not as unstable as a carbocation on, say, an alkyl chain. And the reason for that is this carbocation is capable of resonance. I can have the purple electrons resonating this way. That would put the carbocation here, and I'll show it to you in detail soon. I can have the blue electrons resonating here, putting the carbocation here. But the idea is that the carbocation can resonate within 3 different spots. I have 3 resonance structures. That means it's being shared. That means it's relatively happy, relatively stable, except aromaticity is even more stable. So if I can find a way to make this molecule aromatic again, that'll make it even more stable, which is exactly what happens in the next step. The carbon here has a hydrogen that we don't show when we're looking at line structure, but in this case, we need to show it because we're about to take it away. If I have a base, and this could be any weak base in solution, because aromaticity is so stable that hydrogen is practically being shoved off the molecule. The base will reach for the hydrogen, grab its electrons, grab the nucleus, only the proton. The electrons are left behind, and the electrons are going to collapse towards the carbon to reform the pi bond, towards the carbocation carbon to reform that pi bond. And that will give me a molecule that looks like this. I have my blue and purple pi bonds that hadn't moved. The one that I just showed in pink reformed, but the difference between the reactant and product is that now benzene has an electrophile on it. Now benzene has a substituent that it didn't have to begin with. Are you with me so far? And it looks like we have a mix of both Orgo 1 and Orgo 2 students. Ian, that is an awesome name. That is also my husband's name. So very cool to meet another Ian. So now that we know the basics of the reaction, the intermediate, I told you, has resonance. The intermediate is called the sigma complex. Some of your professors will include it in the question. They'll say, hey, draw the mechanism, include the sigma complex. I want to make sure you know that this is what we're talking about. And this is the overview of the mechanism. Everything else from this point is about understanding what is that super electrophile, what makes it so reactive, and then what we do when the molecule has groups on it already. There are 5 common EAS reactions that you are going to learn, and the mechanism for each one is very detailed. And so to save time, we're not going to go through it because I'd rather focus on practice. Today, we're just going to look more at the basics. So we'll start with just a benzene ring. I'll show you an overview of the reaction, and then I'll show you the super electrophile that we form so you understand why it's so reactive. The first reaction is halogenation. This is the reaction that we hinted at earlier, where I showed you that an alkene will react with Br2, except for benzene to break its aromaticity, we need something a lot more reactive than just Br2. We need to have a good catalyst that will break it apart. And so we'll use Br2 in the presence of FeBr3. You can see any metal with 3 halogens, not any metal, but you'll see a couple of different metals, for example, AlCl3, FeCl3, so any combination that looks like that. And what this is going to do is add not 2, but only 1 halogen to the ring. And the super electrophile that I'm going to put here on the side so you understand why it's reactive in this case is a very unstable halogen intermediate. So we have a halogen with only 6 electrons and a positive charge. If you do a quick formal chart, you'll see that 6 electrons gives me a +1, but it has an incomplete octet. So not only do we have a halogen with a positive charge when halogens prefer to have a negative charge, but it also has an incomplete octet. That's 2 reasons to be unhappy, and that makes it so reactive. That is why the pi bond is going to reach out and attack it. The second reaction that you have to know is aromatic nitration. When you hear the word nitration, what group comes to mind? What are you picturing? Nitration should make you think of a nitro group. A nitro group is an NO2, and the way this happens is if I have HNO3 reacting with a catalyst, you have to have another acid catalyst. And I say another because nitric acid is an acid, but we also need sulfuric acid to drive this reaction forward. The product is going to be a nitro group, NO2, added onto the benzene ring. And what about this intermediate? Or not the intermediate, I'm sorry. What about the reagent makes it so reactive that makes it such a super electrophile? The intermediate looks like this. We have a nitrogen, double bound to an oxygen, double bound to an oxygen with a positive charge. Nitrogen can hold a positive charge, but not as well as something less electronegative, like a carbon. And so even though nitrogen looks like it should want to hold that charge, the oxygens can steal the electron density with resonance, making it even more unstable. And that is why benzene wants to reach out, attack that nitrogen, and ultimately form that nitro group. Now, as we'll see later, the nitro group is neutral overall, but it actually has charges in the neutrality. It's got valence charges, and that makes it a not so ideal group, but we'll come back to that one soon. The next one that I want to look at with you is sulfonation. And sulfonation is one that students sometimes confuse with nitration because of the sulfuric acid, but I want to show you the difference to make sure that you understand. For sulfonation, I have a benzene ring reacting with SO3 in the presence also of H2SO4. The H2SO4 is used to activate it. Whoops, did not mean to erase that. The H2SO4 is used to activate it. And that will give me a product. When you hear sulfonation, I want you to think of sulfate. And the product that we get on the benzene ring is SO3H. So I imagine it as just a hydrogen having come onto the SO3, adding that entire thing. The super electrophile, the intermediate of my reagent that makes it so reactive, is having a sulfur three times double bound to oxygen atoms. The sulfur is very partially positive because it's bound to three very partially negative oxygen atoms, similar to the nitration intermediate, except sulfur, in this case, we're showing it neutral. It can exist with a positive charge through resonance, just like this can have more positive through resonance. Sulfonation, fun fact, is often used as a blocking group. If you have a reaction with something here, and you want to add something here, you put a sulfate, to block that position. You add this right here, and then you remove the blocking group. So some professors will test you on that. I want to make sure you see. The sulfate is big and bulky. If you draw it out, you'll see that sulfur is double bound oxygen, single bound OH. It's big and bulky, and that's what makes it a very, very good blocking group. Let me know in the comments if you learned the blocking groups. Sakura, it is nice to see you. And let's continue. The next reaction, or reactions, I want to show them to you together because everything about the mechanism is pretty much the same. The only difference is that one has a carbonyl and one does not. And that is the Friedel-Crafts reactions, where the first one is an alkylation and the second one is acylation. What is the difference between an alkyl and an acyl group? If you hear alkylation, I want you to think carbon chain. And when you hear acylation, I want you to think of an acyl group, a carbonyl with a halogen, for example, a chlorine sitting on it. The reaction is going to look exactly the same, except for the fact that one's an alkyl and one's an acyl. So let's do a 2-carbon chain for both of them. In alkylation, I have my 2-carbon chain with a chlorine on it. In acylation, 2-carbon chain with a chlorine, but it also has a carbonyl. The catalyst can be exactly the same for both of them, AlCl3, same catalyst that we've seen for the aromatic halogenation. And the product is going to look something like this. So we have our benzene ring. We have our 2-carbon chain. Chlorine came off. Except in acylation, we have a carbonyl. In alkylation, we don't. This is getting a little bit ahead, but we may as well throw it in here. One of the reasons to use acylation over alkylation is alkylation likes to keep going. And because it likes to keep going, it's a little bit harder to control. So one option is to do an acylation and then just cut off the carbonyl to give you the same product without a reaction that keeps going. Jacob, I'm not sure I understand what you meant by your surprising comment. So if you can please elaborate, then I'll be happy to comment on that. So these are, oh, I forgot to give you the super electrophile. We need the super electrophile. What makes the alkylation and acylation, what makes the Friedel-Crafts reaction happen? What is my super electrophile? We said that a carbocation could be stable, meaning carbon holding a positive charge. But this is where I think a lot of professors mislead you. When you learn about carbocation stability, it's not that carbocation stability tells us that a carbocation is stable. Carbocation stability means in the scheme of molecules that have carbocations, which are all unstable, some of them are more stable, or should I say less unstable, because a carbocation as a molecule is unstable. The more substitution, the more resonance, the more stable it is within the realm of understanding that it is unstable. And what we get here for alkylation is an unstable carbocation. For example, here, I just have a 2-carbon chain, CH3, CH2 with a positive charge. Think back to when you learned carbocation stability in the beginning of organic chemistry. You learned tertiary, secondary will form, primary, methyl will not. Well, guess what? Alkylation has a catalyst that will trick this molecule into giving up the halogen and give you a primary or methyl carbocation if needed, which is very unstable, and that is why it's such a super electrophile. With acylation, it gets even worse. You have your carbon, which I'm going to show it as drawn out. You have that carbon, that CH3, bound to that second carbon here, which with the acyl turns into a triple bound carbon to oxygen, a lone pair on the oxygen, and a positive charge. Have you ever seen a carbon triple bound to an oxygen? I'm going to guess before this reaction, no, because it is so unstable. And even though oxygen is the one carrying the charge, ultimately, oxygen is so unstable, it's pulling on the electron density, making the carbon very partially positive, and the carbon is ultimately what gets attacked. And that is why it's the carbon that's attached to the benzene ring and not the oxygen. If you're with me so far, if you follow with the reactions, and more importantly, understanding why these super electrophiles are so unstable and therefore getting attacked by the benzene ring, let me know in the comments. Let me see some hearts in the comments, and we will continue. So you should see a heart by the chat option. There we go. A couple hearts coming in. Awesome. Up to now, we only looked at benzene. So in each of these situations, I give you a benzene ring and I put something on the benzene ring. What happens if there is already something on the molecule? What happens if I have a substituted benzene? For example, I want to do an aromatic halogenation, but I have an OH on it. And I try to react it with Br2 in the presence of AlCl3. Where will that bromine go? I have three choices. So let's draw 3 benzene rings and see where we want to put the product. Let's not forget, I have my OH at the top. And the way we classify the position of the incoming group is by looking at the group compared to what is already there. One option, let's change the color so it stands out. One option is to put the bromine right next to the group that is already there. If I put them next to each other, there's no carbon in between. This is called the ortho position. If I put the bromine one over so that there is a carbon in between the two substituents, this is called the meta position. And if I put it opposite at the other end of the molecule so that there is 2 spaces between them, this is called the para position. I remember I was doing a tutoring session for EAS and it was very late at night, and this is a student I knew well. We had been working together for a while and getting really, really giggly. And somehow, some way, that session turned into this. We have the substituent X that is on your molecule, and we're going to picture X as the hair on this thing. The ortho position is right next to it. These are your eyes. The meta position right here is the mouth, and the para position is this molecule sticking its tongue out at you. So I call this the ortho meta para monster, and this is a fun way to remember in relation to the group that is already there where the other substituents are, meaning what the other substituents are called: ortho, meta, or para. If you like this mnemonic, go ahead and give me a thumbs up in the comments. And then we'll answer the very simple question. How do you know where to add? Do we add something to the ortho, meta, or para position? Okay, for questions about other videos to make, go ahead and email me. That's the best way because then I can discuss it with you in more detail. In order to figure out which position we add it to, you have 2 options. Option 1, you can just memorize the answer. And option 2, you can understand the why behind where they add. And that way, you're never going to get caught off guard. Now, I'm personally going to argue for number 2, especially when you have so much to remember on exams that this is just one more thing you really don't want to memorize. In fact, with final exams coming up, let me know in the comments the date of your upcoming final exam or whatever exam that you're taking. Let's go with number 2. Let's go with understanding. And in order to do that, I want to draw out the sigma complex again, because this is the key to understanding what is going on. So I had used OH before. We'll use the OH again. And to simplify the reaction, I'm just going to show the Br2 with the FeBr3. And then I'm going to put the super electrophile here. So we'll put in a lighter color because it's less the focus. Now I can grab this pi bond and attack the super electrophile. And when I do that, I can have an intermediate that looks like this. My OH is still here. And if this pi bond broke, I can put this super electrophile at this position. I can put this super electrophile at this position. Or if I chose to break this pi bond, whoops, totally missed where that E was drawn. If I choose to break that pi bond, I can put the electrophile at the last position, ortho, meta, or para. And that would be this pi bond broken as follows. Now here is what we want to keep in mind. I'll just put in OMP so you understand where I added it. It's not the position of the electrophile that I actually care about. It's the position of the carbocation that forms as a result of breaking that pi bond. And this is what I want you to pay attention to. Let's put this on another page because I want to have room. If you get nothing else out of today's session, I want you to understand this. So if you've been tuned out, this is where I need you to tune in. In my opinion, this is the most important aspect of what we're doing today. If I put the carbocation at the ortho position, the sigma complex, remember, can have resonance. And that means I can have another resonance structure that looks like this. The purple electrons will jump on over this way. The resonance, let's simplify this because I don't want to keep redrawing that. The resonance will have the purple electrons now sitting over here and the carbocation over here. I can have one more resonance structure where the blue electrons go this way. And that will give me, again, I don't want to redraw the whole thing. That will give me something that looks like this. The blue moved. It is now sitting over here. The carbocation moved. It is now sitting over here. Now, technically, these are the three resonance structures for the sigma complex. But am I done? Do I have only 3 resonance for this intermediate? That was a trick question because the fact that my substituent has a lone pair of electrons, I can do a bonus resonance right here where the electrons from oxygen come down into the ring, taking those electrons up and out of the ring for a 4th resonance. Now, not all molecules will have that 4th resonance, but when they do, they're very, very important. So let's see what that looks like. What changed here? We have a pi bond now here between the carbon and oxygen. The positive charge is sitting on the oxygen, and I'm going to call this bonus resonance because you're not always going to see it, but we do have it in this case. All right. Any questions on what I did here with the resonance? Now here is what I want you to pay attention to. Look at what happened to the carbocation. It started out over here. It never got here because in resonance, the pi bond is sitting in the middle, so the carbocation always skips a position. Notice it went from here to here to here, except when we had the bonus resonance, but on the ring, here, on the ring, here. So if we go back to this version of it, if the carbocation forms here, it can only form here and here. That's really important. If I were to do this entire thing again, and I'm going to challenge you for homework that I want you to work on this. If I start out with a carbocation here for meta, then I would do the same pattern. Skip, carbocation, skip, carbocation like that. And if I do it for para, skip, carbocation, skip, carbocation, same thing. So the first thing I want you to notice, do you see how ortho and para have the same resonance? But the meta has a different resonance. The meta is the reverse pattern. Ortho and para are the same. Okay, this is the most important part of this session, so let me know if you're with me. Let me know if that makes sense. And if you understand that, then this is how I'm going to answer the question from before. How do you know where the incoming substituent will add? Take a look at, the incoming electrophile. Take a look at what you already have on the molecule and ask yourself, what happens to the carbocation intermediate, and how does the substituent behave when that resonance happens? Looking at this molecule, looking at the fact that I have an OH with a lone pair of electrons, do you think that OH would prefer to have the carbocation next to it or far away? Next to it or far away? Well, think about it. If the intermediate is positive, then I have positivity resonating in the ring. If I bring negativity or electronegativity next to the ring, then they will stabilize each other. Opposite charges attract, and having a negative outside the positive intermediate will help it. The OH is considered an electron donating group. What does that mean? An electron donating group is one that donates electrons or electronegativity. It doesn't actually have to have resonance. It donates electronegativity into the ring, and therefore it will stabilize the intermediate. It'll stabilize the sigma complex because we know the sigma complex is positive. And what do you know about the stability of an intermediate? The happier, the more stable, the faster it will form. Because if the intermediate is going to be unstable, it does not want to form. But if the intermediate forming is stable, it'll get there a lot faster. So looking at all three options again, if I can have a carbocation forming next to the oxygen, it is a lot more likely to form. It will form faster. And so that brings us to step 1 of 2 rules. An electron donating group will prefer to add ortho and para. Why does it add ortho and para? Because these are the two positions that bring the carbocation as close to the electron donating group as possible. So that's number 1. And number 2, electron donating groups activate the ring for an EAS reaction. And if we activate the ring, that means it's going to be a faster reaction. The stronger the electron donating group, the more activated the ring, the faster the reaction. So let's go back and look at it right here. When I have a carbocation right next to that OH, that is quite stable. That is how we get the ortho and para directing. What happens if I have a non-electron donating group? What if I have an electron withdrawing group? So what would be a good example of an electron withdrawing group? Actually, before I continue, let's just make sure that we show the products for this reaction. Let's put it right here. Okay, so we saw that it can reach out, and when you have a problem like this, you want to show both products if possible, meaning if it's not possible, obviously you can't if there's a blocking group, for example. So we'll show one product is bromine adding to the ortho position. It doesn't matter if you draw it right or left. And one product, bromine on the para position. 2 different products. Let's jump on over to the electron withdrawing group. An electron withdrawing group is something that pulls electron density out of the ring, and it tries to, what would try to pull negativity away from the ring? Something positive or partially positive. An electron withdrawing group is positive or partially positive. And a very good example, Jerome, thank you, is the nitro group. We already saw nitration from the perspective of adding it, meaning the reaction that puts a nitro group on the ring. But let's take a look at what that actually looks like. If I have a nitro group, NO2, and I draw out all the atoms, so you see exactly what's going on. I have one double bound oxygen that is neutral, one single bound oxygen with 3 lone pairs and a negative charge, formal charge of -1. Nitrogen, no electrons, 4 total bonds. That's a positive charge. Even though the nitro group is neutral, there's a positive charge sitting right there next to the ring. If I try to do the same reaction, let's react once again with Br2 in the presence of FeBr3. And let's see what happens, not to the product. Let's see the intermediate. If I add ortho, meta, or para, and I'm not going to redraw the nitrogen with the charge and everything. I'll just put it as NO2, but hopefully you can clearly see now that the NO2 is plus and minus like this. So we have a positive sitting on the ring. If I break this pi bond, I have the option of adding the incoming electrophile, ortho, or meta. And if I break the lower pi bond, I have the option of adding it para. What do I get as a result? Carbocation here, here, and here. As you will see when you practice, the carbocation can resonate just like I showed you before in every other situation. That means I have the carbocation here, here, and here in resonance. Here, here, and here in resonance. And here, here, and here in resonance. So first we have to take into consideration the fact that the carbocation is a positive sigma complex. We have positivity in the ring right next to a positive group next to the ring. That automatically makes it so unhappy because I have a positive next to a positive. So the first rule with an electron withdrawn group is it's going to slow down the reaction. It deactivates the ring. And I want to make sure you understand. Don't just memorize. Why does it deactivate the ring? It deactivates the ring because we're putting something positive next to a positive intermediate, which is a no-no. I mean, look at this. If I have a positive charge right there, positive near positive, an absolute no. But if I have to do the reaction, it will happen slower, but it can happen. Where is the least evil position to put the carbocation? Meaning, if I have to have a carbocation on the ring, where would you expect to see that? Well, I would want it as far away from the positive nitro group as possible, the positive nitrogen on the nitro group. And because I can't have just one, I have to look at all the resonance. I want to choose the position that does not have a carbocation ever next to the NO2 group. And Jerome, once again, you are absolutely correct. The furthest I can resonate the carbocation is to the right and left. And that means the meta position is preferred if I have an electron withdrawn group. So the electron withdrawn group is considered a meta director, meaning it is meta directing. It directs the incoming nucleophile to the meta position. I want to go back to what I showed you before. Option 1, memorize. Option 2, understand. I know that up to this point, you've probably focused on the memorizing. I challenge you. Do you feel comfortable after you review this again to approach this from an understanding perspective, to say the reason it goes there is because I can picture where the resonance happens, where that carbocation goes, and now I know where it has to add. And the one thing to remember, though, is you don't get a carbocation where the electrophile adds. So the carbocation goes on the in-between position. And so if I'm resonating carbocation here, here, and here, then I have to add it meta. There was a question earlier about adding para to the top. I can't add where I already have a group because I can only add one. I can only have one bond coming out of each carbon on the benzene ring. The rest of the bonds are in the ring itself, meaning there's no hydrogen here to replace and therefore nothing to swap out. All right, so we have our electron donating groups, electron withdrawing groups. There is one exception, and that is the halogen. If I have something like a bromine on the ring, bromine is considered an electron donating group. Halogen is an electron donating group. It puts negativity into the ring and it can absolutely resonate. In fact, one of the resonance structures that would happen when I add ortho or para, so let's put this one here, and I have a carbocation here. If I resonate these electrons here and these electrons here, I'm jumping resonance structures because I specifically want to show you what happens here. And in fact, I want to go one more. These electrons can then come down. What you'll see is something that looks like this. The electrophile having added at the ortho position, the purple electrons moved over to this position, the blue electrons moved over to this position, and now I have the green electrons from bromine down on this position, like this, with a positive charge. Just like the other electron donating groups, the halogen can do a bonus resonance, but, and this is really, really important, the halogen is very, very, very unhappy. Have you ever had a situation where you ask someone to help you? You say, hey, can you come on over? I have to move. I need help moving some boxes out of my dorm room or my apartment. And your friend says, sure, I'll come help you. And they show up. And the entire time, like, oh my goodness, I can't believe I'm wasting a Sunday doing this. These boxes are so heavy. This is so boring. This is such a waste of time. Have you ever had that? And they're just slow and complaining and grumbling and not very helpful, to the point where you're thinking, why are you even here? You're not actually doing anything. Why did you volunteer? Just go home. You're so negative. You're so miserable. I don't need this. That is the halogen. The halogen says, I can take the charge. I can have a positive charge, but this is so unstable and so unhappy and so, Jerome says, my Emma. It's so unhappy that even though it's an electron donating group, and it does direct ortho and para, because that's what these donating groups do, it's ortho and para directing, but it is a deactivating group because it is a miserable, annoying, very unhappy helper. So let me know if that makes sense. And if you understand what is going on with the donating groups, let's do some practice. Okay, so let me know if you're clear on this or if you have any questions, and then we'll jump into some practice. Okay, so let's say I give you a molecule that looks like this. We have just benzene, and you are told somehow, some way, to come up with a reaction that will give you a product that has your benzene ring with, what do we want to put on it? We want to put this group right here, and then this group right here. So we want to put two substituents on the ring. The first thing I want you to do is look at them individually and ask yourself, what kind of a reaction is happening here? How do I do this? Well, this right here is a Friedel-Crafts acylation, because we have an acyl group. And this right here is a halogenation reaction. I can't just start doing the reactions once I identify them, because we have to see where each one is going to direct the next one. Friedel-Crafts acylation gives me an acyl, but the acyl, is it an electron donating group or withdrawing group? Now, most professors will not give you a table on your exam, but in your book, you'll have something like this with hydrogen and all sorts of groups on it, like that. And most students will memorize it and try their absolute best to remember all the different groups that they have to know, in the hopes that you're only tested on one of the ones you've seen. Let me know in the comments if this has been your approach or this is was your planned approach. I'm going to challenge you that you don't need that. What I want you to do instead is look at what you have. Look at the group and ask yourself, does it look like it would donate electronegativity or electron density? Or does it look like it would withdraw? We'll start with the halogen because we've already discussed that. A halogen is an electronegative atom. It has 3 lone pairs of electrons. It most definitely has the ability to donate negativity into the ring. So I recognize that the halogen is an electron donating group. That will be an ortho para director. I know it's an exception, it deactivates, we'll keep that in mind, but in terms of directing effects, it'll go ortho para. This one right here that came from acylation is a carbonyl carbon. Carbonyls can do resonance, and resonance would give me a positive charge at the bottom, making carbon partially positive, a negative charge at the top, making oxygen partially negative, and that means I have a partially positive sitting on the ring. If I have partially positive on the ring, that means that this is an electron withdrawing group. And we know that electron withdrawing groups are meta-directing. So once we identify what the 2 groups are capable of, we then ask, well, which one has to go first? The relationship between them, they're opposite. And if you remember the ortho meta para monster, let's see if I remember where I drew it right there. If you remember the monster, if they're opposite from each other, that is para. This is what I started with. That is para. To get the 2 groups para, I need to put a para director first. I cannot start with acylation. I have to start with halogenation. Once I have halogenation and I have the bromine on the ring, then I can do acylation because the acyl group will wind up at the para position. So if you followed with that, I can then go ahead and fill in my reaction. Step 1, I need the halogen first. That would be Br2 with FeBr3. And then step 2 would be my acylation. And that's where I take this group exactly as I see it. And all I do is add a chlorine at that position. That's the trick. Just cut it right there. Put a chlorine or a bromine at that position. I like to do chlorine because I just pick one and stick with it. And that means I'm going to react it with this group right here in an AlCl3 catalyst. This will add the groups in the correct order to give me the product that I need. Okay, if you have any questions on this, go ahead and type it in. If not, let's do another one. Say I have a benzene ring, and I have to somehow, some way, come up with a reaction that is going to give me, once again, 2 different products on the ring. And the 2 products are going to be, let's make it a little bit tricky. Let's go with this group right here and this group right here. 2 of the same product. Now, professors love to do this. They'll teach a topic. They'll test you on the topic. But by the way, you also have to remember other topics. So you can't just think of this one in a vacuum. But first, we have some questions on the last one. So let's go back. Did I hear you say that acylate is in the para position? The 2 groups are para to each other. So it doesn't matter where on the ring they show up. Instead, you're looking for how many carbons are between them. So let's go back to the ortho meta para monster. I drew it this way, but it's really about how many groups are between them. So notice that for ortho, there is nothing between them. For meta, there is 1 carbon between them. And for para, there are 2 carbons between them. If we go back to the molecule I just showed you, we have a substituent here, and 2 carbons between them. That is how I know we have to add them para to each other, even though they're not drawn one on top and one on the bottom. So Ian, hopefully that answers your question. We have another question. How did you know what catalyst to use? This comes from learning and understanding the reactions. So I only showed you the overview of the reactions, but in my YouTube videos, I actually show you the mechanism for each one step at a time. When we did the halogenation reaction, you can use FeBr3, AlCl3, or anything like that. And then for the acylation reaction, that would be this one right here. So we had an acyl group and AlCl3 as the catalyst. So this is something that you learn, you study, you memorize, but you memorize it only after you study it well and understand it. So let's take a look at what we have here. I have two of the same type of substituent, and my substituent is an alkyl group. It's an alkyl group, which means it would come from Friedel-Crafts alkylation. What do I know about an alkyl group? It does not have any electron pairs on it, meaning it can't do resonance into the ring. But if you remember from way back when you covered carbocation stability, carbons are electron donating groups, mildly electron donating groups. If I have an electron donating group, and we know that that is an ortho para director, well, they're meta to each other. How do I add two para groups? I'm sorry, how do I add two alkyl groups meta to each other if they're electron donating groups? They're ortho para directing. This is a trick question, and this is what professors love to test you on. If it doesn't look possible to do this the way it is, ask yourself, is there another molecule I could have formed that looks kind of like this, but will have a meta-directing effect that I can then turn into this molecule? Well, yes, there is. Because if you already learned your reduction reactions, then you should recognize that you can form a molecule that has just carbon chains with no carbonyls on it, even if you first had carbonyls on it. You have the Clemmensen or Wolff-Kishner reduction. That will completely cleave off the carbonyl and give you the products here. The reason why you would want to go from the carbonyl to not carbonyl is because the carbonyl, you remember, has a partially negative oxygen, a partially positive carbon. These are electron withdrawing groups that are meta-directing. And because they're meta to each other, this is something that I can form. This is something that I cannot. And so the two reductions that you should know, because professors love to test you on this kind of tricky problem in this chapter, are Wolff-Kishner and Clemmensen. One is acid, one is base. So we'll do the Wolff-Kishner here. And that is when you react with N2H4, or professors will sometimes write it as H2N NH2. This is a basic reaction, so you put it in KOH and heat, the triangle representing heat. That completely cleaves off your pi bonds. And then this step is one that we just learned. All we need are the two acyl groups. So we'll have this right here. And you do the reaction twice. So I'll just put 2x for the reaction with AlCl3. You add 1, you add the second one in the meta position, and that will give you the final product here. If I went directly to the alkyl group, then here is what would have happened instead. If I had a benzene ring and I reacted it with the alkylation rather than the acylation reagents, so I had something like this with AlCl3, my first alkylation would give me what I want. Now this is a polyalkylation, meaning the reaction keeps going. Then I could have gotten one at the para position, then I could have gotten one at the ortho position and the other ortho position, and this will just keep going. This is not what I was looking for, and that's why I needed to go the other route. I have quite a few more problems like this, some beginner, some intermediate, at least one or two tricky ones on the worksheet that I created to go with this session. If you go to layerforsci.com/orgoalive, I will email you a link to the worksheet, the notes from tonight, as well as a link to the recording, to this one, and all the other live streams that I've done before. So the worksheet again, layerforSci.com/orgolive with additional practice problems. Now there's one more type of problem that your professors love to test you in this chapter, and that is ranking. What they like to do is rank the rate of the reaction based on different substituents that you have on the molecule. Question, would you be able to go over deactivating ortho para directors, please? Okay, so let's go back to that real quick because I do want to include your question in my upcoming problem. The difference between what we discussed earlier for most of them is I showed you why an electron donating group is an ortho para director. That's this one. And that has to do with getting the carbocation to be directly near that electron donating group, making it as stable as possible. And for some of them, we have bonus resonance. An electron withdrawing group is meta-directing because we do not want a carbocation right there, right next to the NO2, because that's a positive near a positive. So it goes to the meta position. And because it's so unhappy, that deactivates the ring. Electron donating activates, this deactivates. The exception we said are the halogens, because even though they're capable of bonus resonance, they are so unhappy doing it that they just grumble and complain and slow down the entire reaction, making it a deactivated ring, a slower reaction. Keeping this in mind, you may have a question that gives you 5 different molecules with 5 different substituents, and you have to rank it from the most to least reactive towards electrophilic aromatic substitution. Or you might get something like, which of the following is going to react fastest with bromine in the presence of whatever, implying rank them from activating to deactivating. So let's come up with a couple of different substituents to rank. We'll put a hydrogen. We'll have a carboxylic acid. We'll have an ester. We'll have an OH, and we'll put a bromine. Okay, so each of these should remind you of something that we have already seen. So let's go through them one step at a time. And remember, option 1, memorization. Option 2, understanding. We're going with the understanding portion. We had talked about electron donating and withdrawing, but what about hydrogen? Where does hydrogen rank? Because it's not a donating group and it's not a withdrawing group. So what do I do about hydrogen? Do you know how to rank hydrogen? This is a trick question. Consider hydrogen as your 0. Meaning, if something is activated, it is more reactive than hydrogen, which is my 0. If something is deactivating, like an NO2, it is less reactive than hydrogen, which is my 0. So hydrogen is the thing we compare against. So we're going to put hydrogen as 0, and then let's see what the rest do in terms of activating or deactivating. For the carboxylic acid, again, I don't want you to refer to any table. I didn't even think to copy a table to show you today because I'm so against the table. I want you to look at it and ask yourself, donating or withdrawing? What do you see on the carboxylic acid that will give you a clue about how it will react? Directly attached to the benzene ring is a carbonyl. We've already seen that a carbonyl has a partially negative oxygen and a partially positive carbon. That carbon is an electron withdrawing group because it's partially positive. At this point, that's all I'm ranking, donating or withdrawing. That's it. And we'll come back and classify them in more detail after. The next one is also a carbonyl, but the carbonyl is not directly attached to the benzene ring. It's an oxygen with lone electron pairs that are capable of resonance that are attached. Resonating electrons are electron donating. These are activating. Let's also put right here. So electron withdrawing, I'll just put deact for deactivating. This right here is activating. The OH we've seen already in the previous examples. It's got the lone pairs. Brenda, exactly. The lone pairs can resonate into the ring. That will stabilize the carbocation intermediate. That will make the reaction go faster. OH is an electron donating group. It is activating. And finally, we have halogen. Halogen is our very grumbly friend. Even though it is an electron donating group, it is a deactivator because it is very, very unhappy. And the way I like to approach these problems is to rank them based on what I know for sure and then compare them in more detail. So I know for sure that hydrogen is going to be in the middle. And then anything that is deactivating is going to be to the right of hydrogen. So that'll be the carboxy and the bromine. Now, the bromine is deactivating. We didn't talk about it in more detail, but it is slightly deactivating. Your friend who grumbles the entire time and barely helps you, it's still somebody helping you. So they're almost worth the space that they take up. And therefore, even though bromine is a deactivator, it is very, very mildly deactivating, and it's just slightly less reactive than hydrogen. And therefore, the carboxylic acid is going to be the most deactivating of this group, and this will be the slowest. So now let's look at the other side. I told you no table. Most students will look at this and go, oxygen to resonate, oxygen to resonate. How do I know which one if I don't have a table or I haven't memorized the table? Very simple. Ask yourself, what is actually going on here? If oxygen is resonating electrons into the ring, is it able to fully donate its electrons or not? Something like this, an ester, an amide, you can also see an amide like this. If the oxygen or nitrogen is attached to the ring, it can resonate into the ring, but this is your friend coming over to help you, but they won't put their phone down. They keep checking TikTok. They just keep browsing and being distracted and not quite there. It can resonate into the ring, but it can also resonate up this way. It's distracted. And that means as much as your friend is going to help you more than this one, your friend is happy to help you. They just keep checking their notifications. It's not going to be as activating. And so based on logic, no table, we know that OH is going to be the fastest. And then the ester, then hydrogen, then bromine, then the carboxylic acid. So this will be the fastest. And if we want to rank it here, from fastest will be speed 1 and slowest will be speed 5, because sometimes your professors won't give it to you like this. They'll just have you put numbers here. Now that we know what they are, let's go through it in more detail. The absolute fastest is having an OH, pure focus on resonance. The second, why am I putting a 5? 1 is the fastest. The second fastest is the one that can resonate but is slightly distracted. The third one is hydrogen, which is my ground zero. The fourth one is bromine, which is a deactivator but very, very mild. And the last one is a carboxylic acid because it has that partially positive carbon and it is not very happy. Question: activating and deactivating nature is based on electromeric effect. The idea with activating and deactivating, I don't want you to memorize any fancy definition. I want you to look at it and ask yourself, am I putting negativity into the ring where the negativity will stabilize that carbocation intermediate? The more negativity I can put towards the ring, the more I stabilize that carbocation, the faster it is. Deactivating is putting positivity near the ring. I do not want to have a positive charge near a positive charge. And so the more positive or partially positive my substituent, the more I deactivate the ring because of how unhappy it's going to be. So Spaceflock, I hope that answers your question. How do I get around memorizing? Okay, so this is not related to today. Let's keep the question specific to carboxylic acid. What am I talking about? To electrophilic aromatic substitution. Now this right here is the start of this topic. Make sure you go back and review. Make sure you try the worksheet that I have created for you. You just go to the link on the screen, laborforsight.com/orgolive. If you want even more help with this topic, oops, With this topic and any other organic chemistry 1 or 2 topic, I cover everything in more detail in my organic chemistry study hall. leahforsci.com/join. That is where you can sign up. The link again, leahforsci.com/join.